INFORE is a project that aims to make extreme scale analytics and forecasting accessible to everyone. INFORE targets data analysts who are often not expert programmers and enables them to design data processing workflows that can be executed over a variety of available big data platforms or HPC infrastructures. These workflows are then processed by an optimizer, which decides which part of the workflow will be executed over which data platform. INFORE has developed extremely scalable techniques and tools for online machine learning and data mining, for data summarization, and for forecasting future events of interest. The project is evaluated over 3 real-world use cases from the life sciences, financial, and maritime domains. INFORE brings together a consortium of 9 partners from 5 different countries. The project is coordinated by the Athena Research Center.
Consider that we have a number of geographically dispersed computer clusters, each running diverse data technologies, and we want to execute global extreme-scale analytics applications over such infrastructures. These analytics are destined to run for protracted periods of time, and they are to provide results in an online real-time fashion. If we allow the application to manually decide the clusters, the big data platforms, and the resources they should receive, their decisions will be suboptimal, or they won't be able to decide at all given the complexity of the system. Therefore, in INFORE, we provide an optimizer that automates such decisions, ensuring that each application runs with interactive response times, not only when they begin, but also in the long run.
How do you forecast a collision at sea? How can you forecast fraud in financial transactions? How can you forecast whether a drug treatment can be effective in silico experiments? In all of these application domains, custom tools are necessary for complex event forecasting. However, such a customization process can be tedious and error-prone. In order to address this issue, we have developed a formal computational framework for complex event forecasting. This framework is generic enough that may be used in a wide class of application domains. For example, in the life sciences use case of the INFORE project, our formal computational framework for complex event forecasting can achieve predictive accuracy of approximately 80%, while at the same time reduce computation time by more than half.
The aim of the INFORE architecture is to combine graphical workflow design and the computational power of real-time streaming platforms. The RapidMiner workflow designer already allows to design and execute machine learning processes without the need to write a single line of code. Now we use this design principle to create workflows that analyze streaming data on Apache Flink or Spark clusters. Connection objects that can store and test the connectivity to different clusters help to easily manage multiple deployments and systems. The same connection objects are used to get data in and out via Apache Kafka and to communicate with specialized analytical components developed by our project partners. It's also possible to deploy any RapidMiner model on a cluster to directly score streaming data. The design processes are platform independent, so they can run on a Flink or Spark cluster without any changes and can even be split between multiple execution engines.
In the life science use case of INFORE, we have significantly advanced the state-of-the-art in multi-scale model and simulation of tumor growth and their application in the study of efficient treatments that avoid the emergence of resistant cells. For this purpose, we have integrated the multi-scale simulator into an HPC-based model exploration workflow to enable the efficient parameter calibration, hypothesis testing, and uncertainty quantification of different cancer models. Moreover, our workflow, based on IMUs and Physibos, produces a large-scale data streams of simulated outputs ranging from 10 megabytes an hour to 100 gigabytes a minute, depending on the complexity of the model. To cope with this large-scale data stream, we have adapted the INFORE architecture to enable our workflow to perform online model exploration. This novel approach uses complex event forecast and filtering methods to quickly discard uninformative simulations, reducing computing times to 30% and accelerating the in silico identification of promising therapies.
Another aspect of our work has been focused on developing a deep neural network architecture to predict the future behavior of a gene regulatory system. The idea is to forecast the time trace of such a system and infer the gene regulatory interactions. The results had an high accuracy on the prediction, and moreover, looking at the layer of the network, we are able to discern between different gene regulatory network architectures. These results has been published in peer-reviewed journals and opened a pioneer research in this field.
Another aspect of our research during pandemic relates to SARS-CoV-2 structure interactions with proteins. We made use of algorithms and exploited synopsis to make fast and parallel calculations. The results have been published in a high-level journal of precise research and are available also to non-expert users through our web pages.
At Spring Techno, we had the big challenge of high financial data load necessary to get an edge in the financial markets and risk analysis. Approximately 1.5 billion messages are added every day, with yearly data growth rates estimated at 30 to 50%. The main focus of the financial use case is on forecasting price swings, systemic risk prediction, and decision support for investment opportunities. These were tackled by INFORE big data technology, and as a result, big data filtering, for example, runs now 50% faster than before. Our surveys show that the results were very well received by our target audience of traders, banks, and brokers.
The Maritime Situation Awareness use case of INFORE aims at combining global views of maritime data, such as the marine traffic, ice data, and satellite imagery data, with local views of data, as for example acoustic data coming from local sensors, in order to obtain a global picture of the maritime domain. So, for example, we have implemented workflows that automatically detect vessels in satellite imagery using neural networks, and we combine this data with AIS in order to detect vessels that have switched off their AIS transponders. We also implement data science workflows in order to detect and forecast maritime events in real time, and we display the results of these workflows using a web-based interface.
To be able to combine different sources of vessel tracking data in a scalable way, we have implemented the Fusion engine, which is able to automatically assign data source agnostic vessel positions to tracks. This enables us to identify vessels in multiple data sources and fill in the missing positions of one data source with data coming from another data source, thus creating unified trajectories of vessels. To address the performance requirements of data fusion in real time and on a global scale, we implemented the Fusion engine as a distributed system relying on big data technologies such as the ACA framework.
In this map, we are able to see in real time the output data from the INFORE models, such as the latest position of the vessels, as well as the occurring detected simple and forecasted events in the relevancy area of interest. The monitoring is as easy as by just panning across the map, and by hovering and clicking on the vessel markers, the user is able to see some extra information about the vessel. The same is also for the events, just like this as we can see here. Now, one way of discovering the occurred maritime events is just by panning across the map, and also another way for convenience is by checking all the occurred events in this list, where the user can click on each card, having the map zoom into the event's position.
The sea trial was held off the coast of Porto Venere, Italy, in February 2022. The objective of the trial was to validate the INFORE system for the maritime use case in real-world conditions. The INFORE system uses global view sensors such as AIS and satellite imaging. The produced measurements are scrutinized through machine learning algorithms and trigger the local view sensors in case an anomaly is detected, for instance if a vessel switches her AIS off. Local view sensors consist of hybrid heterogeneous robotic networks composed of an onshore thermal and RGB camera and multiple autonomous robots equipped with passive sonar sensors. The objective of the network is to detect and localize non-cooperative targets. Robot autonomous decision-making is central to control the network operations, which adapts its configuration for improving target detection and localization. The produced measurements inform the INFORE MSA system, enabling complex event detection, for instance confirming that a vessel is fishing in a forbidden area. The INFORE results pave the way towards the development of smarter, autonomous, heterogeneous robotic networks for different MSA applications.